Last time I did this problem without friction. And this time we want to now assume that there is a coefficient of kinetic friction between the blocks and the ground, and it's 0.20. These blocks have the same masses as before, and before they had the masses of M1 was 8 kilograms, M3 was 9 kilograms, and then M2 ended up being 14.8. So M2 is 14.8 kilograms. So even though it's smaller, it may be just more dense or something. But anyway, what we want to do now is consider friction in the motion. So we're going to apply 108 Newton force to block 1. What will be the new acceleration when the blocks are in motion and the new normal forces between those blocks? So last time I calculated that there was going to be 108 newtons applied by the person on the left. 80.9 of those newtons would be used to push blocks 2 and 3. And the idea is that block 1 is in contact with M2, and it has to push all of this stuff to the right. So whatever proportion of mass that is, that's how much block 1 is responsible for pushing. And there's a formula for this, which I call M cart over M system, and then you multiply that ratio times the force that's applied. The proportion of mass that you're pushing here, that goes in the numerator, so it would be M2 plus M3 is what I'm calling the cart. And then the total system mass here would be M1 plus M2 plus M3. So it's a proportion, and then you multiply by the force applied. And that apparently is going to be 80.9 newtons, is what it ends up being. Then what you do is you figure that M2 has to push just M3. And so to get that final normal force of 30.6, what you would do is just put M3 out of the total. Now you might be wondering, why do I call it a cart? Well, I guess you could think of like shopping at the grocery store. It's something you push. But not only that, but the formula also applies to when we have a cart on a surface where there's a hanging mass hanging over the edge. And so this would be the cart in that situation. And if the cart was like M1 and this was M2, then you could still use the same formula. M1 out of M1 plus M2 times the force that's being applied to this situation. So it's a very versatile formula. And we can try to use it here in this example with friction as well. Alright, so let's set it up. One of the things we want to do is analyze a system of our choice. And I'll start with the easiest case. I'll start with just letting the whole thing be the system. Alright, now we can draw a free body diagram for that system. So there will be a weight to it, Fg, and a normal force. Now this time I'm going to calculate what the weight is. To do that, we would use the formula Fg equals mg. So that'll be m1 plus m2 plus m3 times g. So let's get all the mass here. Let's see what that comes out to. 312 newtons. Alright, so in order to balance forces in the y dimension, the normal force also has to be 312 newtons. Now, we want to throw in the push as well, which we know is 108 newtons. And this time there's going to be one more force. It's going to be a force which resists motion, and that is the force of kinetic friction. So since our block is presumably going to accelerate to the right when the person pushes, what we'll have is we'll have a force in the opposite direction that's going against the push. Alright, and that force is called force of kinetic friction, Fk. And there's going to be a formula for calculating kinetic friction. What it is you use what's called a coefficient of kinetic friction, mu k, times the normal force. Those are the things that are involved. So the mu k is just a property of the materials involved and like how they interact. So we got like wood and some kind of tile or something. And then it also depends on the normal force of how much force there is between these surfaces. So the harder they're being pressed together, the more friction there could be. So that's why I calculated the normal force, because I need that to calculate the friction. So let's plug in. We'll have Fk equals 0.2. That was the coefficient of kinetic friction they gave here. And we'll multiply by the 312 newtons, so it's going to be 62.3 newtons. And so what this means is the system will not accelerate quite as strongly as it did before. Before, they told us that the acceleration was 3.4 meters per second squared. So we may wish to find the new acceleration. And to do that, we want to use Newton's second law. So what does Newton's second law say? It says F net equals ma. But we have to calculate what F net is. So in order to get F net, we want to sum all the forces that are happening in this problem. We don't really care about the y dimension though, because we can see clearly those forces are balanced. So what I really need is I need the net force in the x direction. That's what matters to the acceleration. It's like I know the acceleration in the y dimension is 0, but I want to calculate the x component of it. So for that, what we want to do is sum the forces. So we'll have Fk plus F push. Now, why do I put x's on them? because x lets me keep track of the signs, and the signs are important here. If I don't have x's on there, I shouldn't include signs, technically, because they would be magnitudes if I didn't put the x on there. It's a very subtle thing that sometimes eludes people. Understandably, it took me many years to figure it out. Alright, so let's put negative 62.3 plus 108. That way we're getting the net force in the x direction. $45.7. Okay, now that's something we can plug in and find the new acceleration. The total mass of the thing is 31.7. Alright, so that cuts our acceleration down to 1.44 meters per second squared, just because of the presence of the friction. Alright, now that we have that, we want to go through the same process as before to find the normal forces between the blocks. And so let's draw our system again. This time we can let just the last block be the system. It's often the best choice because this one's going to have the fewest number of forces on it of all the blocks, because he's not like sandwiched between other things. So he's the easiest one to analyze. Alright, so what are the forces that are going to be on it? Okay, we're going to have a forward push here. That'll be F of 2 on 3, it's called. But it'll also be experiencing friction as well. The friction that it feels will be in proportion to its mass. So its mass is less than the overall mass. So it's going to be less friction than the overall blocks would have felt. So the overall system had 62.3 newtons for the whole thing. So this will be less than that. You could call it perhaps FK3, so you know that it's the kinetic friction just on block 3. Alright, now we could say FK3 equals mu k times Fn3, where Fn3 stands for the normal force acting on block 3. Alright, so this would be the normal force. This is the weight of it. So we better calculate the weight of it. So we're basically going to need 0.2, and then we can do M3, which is 9 kilograms, times G. Alright, so this is basically going to be the weight of M3, and it's also going to be the normal force acting on M3. I get 17.64 newtons for that. Alright. Now, since we know that, we'll be able to solve for what we want, which is F of 2 on 3. Okay, so we know that Fk is 17.64. So how do we solve for F2 on 3? Well, you want to use the net force on the system to do it. Alright, so what's the net force? F net on 3 equals M3 times A3. I'm going to apply Newton's second law to my system. But notice that the net force is a combination of two forces, Fk3 and F2 on 3. So one option would be to do this, F2 on 3 minus Fk3 to get our net force equals M3 times A. All right, one of these things is going to be unknown, but we actually know everything else. The one that's unknown, of course, is this one. Let's see if we can plug everything else in. Keep in mind that when I write it this way, though, these are magnitudes. All right, this is treated as positive now because I didn't put the x on it. And so we'll end up getting a positive number, which is what we need. Let's see. So let's do F2 on 3 minus 17.6 equals 9 kilograms times the acceleration, which we had calculated before, of 1.44 meters per second squared. Let's see what we get then for F2 on 3. All right, I'm getting 30.6 newtons. Interestingly, same as it was before. And so by Newton's third law, the force of 3 on 2, the reaction force, will also be 30.6 newtons. All right, so what is the explanation for like why it's the same? It's because the M3 still occupies 9 kilograms out of the total of 31.7. So you could still do the M cart over M system approach and then multiply by the force that's applied, which would be the push. So if you did that, you would get 9 kilograms divided by the total 31.7 and then multiply by 108. You still get 30.6 newtons, so it's a fraction of the original applied force. But notice we do have a smaller acceleration, so that's the change that we really see when we incorporate the friction. All right, so what does that mean? Let's do one more calculation for the middle block, though, because I feel like that's a tricky one to calculate. I mean, even though we know the answer is actually going to be the same as before, let's just calculate it quick. All right, so to do that, you want to make a new drawing. Where now all this is the system. It is the thing being pushed. So we draw a free body diagram for it. it has a weight. I'll call it FG23 because it's a combination of blocks 2 and 3. There's going to be a normal force, FN23. There will be a push of F1 on 2, 3, you could call it. Or I'll just call it F1 on 2, that's fine. And then there'll be some friction. FK23. Alright, go through all the calculations. So the weight will be M2 plus M3 times G. And that's going to be 14.8 plus 9 times 9.8 233 newtons. So the normal force is also 233 newtons. Alright, let's find the friction now. You want the kinetic coefficient of friction times the normal force for both these blocks. So that's going to be 0.2 times our 233 newtons, 46.6 newtons. Alright, now we would do the same thing as before. Set up a Newton's second law equation. And apply it to just the system in question. Alright, now we can sum and difference the forces. So F1 on 2 is the larger of the two. We'll subtract the smaller here of FK23, M23, A23. They all have the same acceleration in common. And I get that F1 on 2 is, not surprisingly, 80.9 newtons. So we could have used the shortcut formula, of course. And the shortcut formula would be that F1 on 2 will be that fraction of the mass of the things that we're pushing divided by the total system mass, and then times the force that's applied by the person or whoever's doing the pushing. So we would get 14.8 plus 9 over 8 plus 14.8 plus 9 multiplied by the 108 newtons applied. And you get 80.9 newtons out of that.